Look up at the night sky, what do you see? A scattering of stars, maybe a planet or two, but beyond that, an endless, invisible ocean of mystery. The universe we live in isn't just vast, it's growing. Every second, every minute, the space between galaxies stretches wider, carrying them farther apart like dots on an inflating balloon. And here's the thing that'll twist your mind: this expansion isn't just happening somewhere out there. It's happening right here, right now, all around us. The fabric of reality itself is stretching, and we're riding that cosmic wave without even feeling it. Think about that for a moment. The universe began as a single, unimaginably dense point nearly 13.8 billion years ago, a spark that ignited everything we know. And since that moment, space has been expanding in all directions, carrying galaxies along with it like leaves caught in a river's current. But here's where it gets even stranger. The farther away a galaxy is, the faster it seems to be moving away from us. It's as if the universe is in a hurry to get somewhere we can't even see. This isn't just some abstract idea, it's the reality we live in, a reality that defies our everyday intuition about how things should work. So what does this mean for us here on our tiny pale blue dot? It means we're part of something far grander than we can fully grasp. Over the next 25 astounding facts, we're going to peel back the layers of this cosmic mystery. We'll explore how the universe's expansion was discovered, why it's speeding up instead of slowing down, and what that tells us about the fate of everything: stars, planets, even time itself. This isn't just a story about distant galaxies, it's your story because you're woven into this unfolding tapestry of space and time, so buckle up. By the end of this journey, the night sky will never look the same to you again. Here's something that sounds impossible but is absolutely true: the universe is expanding faster than light, not just in some far-off corner of space, but everywhere, all at once. How can that be? After all, Einstein taught us nothing can move through space faster than light. The key lies in understanding that this expansion isn't about galaxies speeding through space like rockets, it's about space itself stretching, carrying galaxies apart like raisins in rising bread dough. Take Hubble's law, for example. Back in the 1920s, astronomer Edwin Hubble noticed something bizarre. The farther away a galaxy was, the more its light shifted toward the red end of the spectrum. This redshift wasn't just random, it revealed those galaxies were moving away from us, and the most distant ones were fleeing the fastest. But here's the twist: it's not that those galaxies are actively speeding through space. Instead, the space between us and them is growing, pushing them away faster the more distance there is to stretch. Now, imagine two ants sitting on a rubber band. If you slowly stretch the band, the ants drift apart even though neither is walking. Now picture that rubber band stretching so fast that the distance between them grows quicker than an ant could ever crawl. That's what's happening on a cosmic scale. Over vast enough distances, space expands so rapidly that galaxies effectively recede faster than light, and this isn't some theoretical edge case, it's happening right now, meaning entire regions of the universe are disappearing beyond our cosmic horizon forever, lost to the relentless stretching of space. What does this mean for us? For one, it shatters our everyday intuition about speed and distance. Light might be the ultimate speed limit for objects moving through space, but space itself plays by different rules. It can stretch without breaking any cosmic laws. And this isn't just a curiosity, it shapes the fate of the universe. As expansion accelerates, distant galaxies will vanish from view entirely, leaving future astronomers with a far emptier sky. The universe, it seems, is in a hurry to keep its deepest secrets just out of reach. If the stretching universe were a mystery, dark energy is its most baffling clue. This invisible force makes up roughly 68% of the cosmos, yet we still don't know what it actually is. What we do know, it's the reason the universe isn't just expanding, it's doing so faster and faster, as if some unseen hand is pressing down on the cosmic accelerator. The story of dark energy's discovery reads like a scientific detective novel. In the late 1990s, two separate teams of astronomers were studying distant supernova exploding stars that act as cosmic mile markers. They expected to find these stellar explosions dimmer than predicted, evidence that the universe's expansion was slowing down over time, tugged by gravity's relentless pull. Instead, the opposite was true. These supernovae were fainter than they should have been, meaning they were farther away than anyone anticipated. The universe wasn't just coasting, it was speeding up, as if some invisible force was flinging galaxies apart. Here's where it gets even stranger. Dark energy isn't just powerful, it's fundamentally unlike anything else in physics. Unlike matter or radiation, which dilute as the universe expands, dark energy's density stays constant. Imagine filling a balloon with air. As it inflates, the air inside thins out unless, somehow, new air magically appears to keep the pressure steady. That's dark energy in a nutshell, a cosmic phenomenon that seems to generate more of itself as space stretches, pushing galaxies apart with ever-increasing force. What could possibly explain this? One leading theory points to the fabric of space itself. Quantum physics suggests that empty space isn't truly empty, it's a seething foam of virtual particles popping in and out of existence. Could dark energy be the energy of empty space? A cosmic background hum with repulsive gravity? Maybe, but here's the catch. When physicists calculate how strong this vacuum energy should be, the numbers are off by a factor of 1 followed by 120 zeros. That's not just a rounding error, it's the biggest mismatch between theory and observation in all of science. So where does that leave us? In a universe where the dominant force remains utterly mysterious, shaping everything from the fate of galaxies to the ultimate destiny of reality itself. One thing's certain, dark energy isn't just a footnote in cosmology, it's the invisible architect of our expanding cosmos, silently rewriting the rules of the universe while we scramble to understand them. Even in a universe that stretches beyond imagination, there's a boundary to what we can ever see, an edge to our cosmic vision. The observable universe extends roughly 93 billion light-years in all directions, not because that's where space ends, but because that's as far as light has had time to reach us since the dawn of time. Picture standing in the middle of an endless foggy plain. No matter how sharp your eyesight, there's a point where the mist swallows everything, not because the plane stops, but because the light from distant objects gets lost along the way. That's our cosmic predicament. This limit exists for two mind-bending reasons. First, the universe is only 13.8 billion years old, so you might assume the farthest light we could see traveled 13.8 billion light-years. But here's the twist, space itself has been expanding all that time, stretching the distance that light had to cover. Imagine a photon emitted by an ancient galaxy shortly after the Big Bang. As it races toward us, the space behind it stretches like a treadmill speeding up, forcing the light to run even farther. By the time it arrives, its starting point isn't 13.8 billion light-years away, it's 46 billion, thanks to expansion. And because the universe grows in all directions, doubling that gives us our 93 billion light-year cosmic horizon. But what's beyond that? Not just more galaxies we can't yet see. Thanks to dark energy's relentless push, some regions of space are receding so fast their light will never reach us. It's like a ship sailing away from shore faster than the waves it creates can travel back. Those waves, the light from those galaxies, will simply never arrive. This means we're forever cut off from vast reaches of the universe. No matter how powerful our telescopes become, here's the real kicker: as expansion accelerates, our observable universe is actually shrinking over time. Distant galaxies that are barely visible today will one day vanish from our skies entirely, their light stretched into useless infrared whispers, then into nothingness. Future civilizations might gaze up at a far lonelier cosmos, unaware of the countless galaxies that once dotted the darkness. We're living in a privileged sliver of time, able to see just enough of the universe to know how much we're missing, a cosmic tease written in the fading light of the stars. Here's something that might bend your perception of reality. The universe, in all its vastness, appears to be flat, not flat like a sheet of paper, but flat in the geometric sense, where parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. This isn't just some abstract math puzzle, it's a fundamental property of the cosmos, etched into the afterglow of the Big Bang itself. How do we know this? The answer lies in the cosmic microwave background, the oldest light in the universe. Picture this faint glow as a snapshot of the infant cosmos, taken when the universe was just 380,000 years old. By studying subtle temperature variations in this ancient light, scientists can deduce the universe's shape much like a surveyor measures the curvature of the Earth. And the results are startling. No matter how precise our instruments get, the data overwhelmingly points to a flat universe. Think of it this way: if space had positive curvature, like the surface of a balloon, parallel lines would eventually converge. If it had negative curvature, like a saddle, they'd diverge, but in our reality, they stay perfectly parallel across incomprehensible distances. This flatness isn't just a lucky coincidence, it's a critical clue about the universe's origins. During the Big Bang, an unimaginably rapid period of expansion called inflation likely stretched space so thin that any initial curvature was smoothed out, leaving behind the flat cosmos we observe today. Here's where it gets even stranger. A flat universe suggests something profound about its fate. It could expand forever, thinning out into cold darkness. But it also raises a tantalizing question: is our universe truly infinite, or just so unimaginably vast that its curvature is too subtle to measure? For now, the answer remains written in the fading whisper of the Big Bang's afterglow, waiting for us to decode its next secret. Now let's rewind the cosmic clock to the very beginning, not just to the Big Bang, but to a fraction of a second after it, when the universe pulled off its most spectacular magic trick. Picture this: in less time than it takes light to cross a single atom, the entire cosmos ballooned from smaller than a proton to the size of a grapefruit. This wasn't just rapid growth, it was exponential, unimaginable expansion, a burst of cosmic inflation that set the stage for everything we see today. What's astonishing isn't just the speed, it's what inflation explains about the universe's eerie uniformity. Look in any direction, and the cosmic microwave background, the afterglow of the Big Bang, is almost perfectly smooth, with temperature variations no greater than 1 part in 100,000. Without inflation, this makes no sense. Regions of space now billions of light-years apart were once too far apart for heat to evenly distribute, like 2 cups of coffee placed miles apart somehow ending up at exactly the same temperature. Inflation solves this by proposing that these regions were right next to each other before the universe stretched them apart in that split-second surge, locking in that uniformity before space went rogue. But how? Think of the early universe as a bubble of unimaginably dense energy, teetering on a knife's edge between stability and chaos. A quantum fluctuation, a random flicker in that energy triggered a phase transition, like water suddenly flash freezing into ice. This released a burst of repulsive gravity, a kind of anti-gravity that sent space itself into hyperdrive. For that fleeting moment, the universe wasn't just expanding, it was doubling in size over and over again, perhaps 100 times in a row, each doubling happening in around 10 to the power of negative 37 seconds. By the time inflation stopped, the cosmos was vast enough to contain every galaxy, star, and planet we'd ever discover. Here's the wildest part: inflation didn't just smooth things out, it also planted the seeds for all structure in the universe. Those tiny quantum fluctuations, they got stretched too, becoming microscopic hills and valleys in the fabric of space. Over billions of years, gravity amplified those imperfections, pulling matter into the valleys to form galaxies, while the hills became the vast cosmic voids between them. Without those random quantum ripples blown up to cosmic scale by inflation, the universe would be a featureless sea of particles, no stars, no planets, no us. Yet for all its explanatory power, inflation remains a theory, one with competing versions and unanswered questions. Why did it start? What stopped it? Some models suggest our universe is just one bubble in an endless froth of inflating space, each with its own laws of physics. Others propose that inflation never truly ends, with distant regions of space still undergoing exponential expansion, spawning new universes beyond our horizon. One thing's certain, those first moments of cosmic inflation weren't just a footnote in history, they were the ultimate architect, shaping a universe where randomness and order dance together on the largest scales imaginable. Hidden in the vast cosmic theater, there's an unseen puppeteer pulling the strings: dark matter. This mysterious substance outnumbers ordinary matter 5 to 1, making up roughly 27% of the universe, yet it refuses to show itself. It doesn't emit, absorb, or reflect light. You could stare straight through a mountain of it and see nothing but empty space, but don't let its invisibility fool you. Dark matter is the cosmic glue holding galaxies together, the hidden scaffold upon which the visible universe is built. The first clues to its existence came from something as simple as watching stars whirl around galaxies. In the 1930s, astronomer Fritz Zwicky noticed something bizarre. Galaxies in the Coma cluster were moving so fast that they should have flown apart, like a merry-go-round spinning so violently its riders would go flying. Yet they stayed bound together, defying the laws of gravity as we knew them. The only explanation: some invisible mass was lurking in the shadows, its gravitational grip strong enough to keep everything in place. Decades later, Vera Rubin's observations of spiral galaxies confirmed its stars at the edges orbited just as fast as those near the center, as if gripped by an unseen hand. Without dark matter's gravitational anchor, galaxies would unravel like yarn in a hurricane. But what is it? Leading theories suggest dark matter could be made of weakly interacting massive particles, hypothetical entities that barely interact with ordinary matter except through gravity. Or perhaps its actions, ultralight particles drifting like a cosmic fog. There's even a wildcard idea that dark matter isn't particles at all but primordial black holes, relics from the universe's first seconds. Yet after decades of searching, we've never directly detected it. Experiments like the Large Underground Xenon detector operate miles beneath the Earth, shielded from cosmic noise, waiting for the faintest tick of a dark matter collision. So far, silence. Here's where the plot thickens. Dark matter doesn't just hold galaxies together, it shaped the universe's very architecture. After the Big Bang, ordinary matter was too hot and energetic to clump efficiently. Dark matter, unaffected by light or heat, formed vast invisible webs, gravitational wells that drew in gas and dust like water swirling down a drain. Without these hidden scaffolds, galaxies would have been scattered randomly, a cosmic soup with no structure. Yet for all its importance, dark matter remains a ghost. We see its shadow in the bending of light around galaxies' gravitational lensing, where invisible mass warps spacetime like a fingerprint pressed on glass. We map its distribution in the cosmic microwave background's faint imprints, but until we catch it in the lab, dark matter remains the universe's ultimate cold case, an enigma woven into the fabric of reality, unseen but undeniably real. One thing's certain, solving this mystery wouldn't just rewrite physics textbooks, it would reveal the hidden machinery behind everything we see and everything we don't. The night Edwin Hubble peered through the Hooker telescope in 1829, he wasn't just observing galaxies, he was unraveling one of the universe's best-kept secrets. What he discovered would rewrite our cosmic story forever. By measuring the light from distant spiral nebulae, Hubble noticed something peculiar. Their glow wasn't just dimmer than expected, it was shifted toward the red end of the spectrum, like a cosmic siren sliding into a lower pitch. This redshift wasn't random noise, it was a fingerprint of motion. revealing that these so-called nebulae weren't just distant objects, they were racing away from us, carrying the fabric of space itself along for the ride. Redshift works much like the Doppler effect you experience with sound. When an ambulance speeds toward you, its siren sounds higher pitched. As it races away, the pitch drops. Light behaves similarly. When a galaxy moves toward us, its light compresses into shorter, bluer wavelengths, but Hubble's observations showed the opposite: light stretched into longer, redder wavelengths, meaning galaxies were receding. The farther away a galaxy was, the greater its redshift, as if the universe were a vast loaf of raisin bread baking in an oven, with each raisin or galaxy carried farther from the others as the dough space expanded. But here's what stunned scientists: this wasn't just galaxies moving through space. Hubble's data revealed a linear relationship between distance and velocity, now called Hubble's law, proving space itself was stretching. Picture two dots on a deflated balloon. As you inflate it, the dots drift apart not because they're moving across the surface, but because the rubber between them stretches. That's precisely what's happening across cosmic scales. The more space between two galaxies, the faster they separate, not from any force acting on them, but because there's simply more rubber to stretch. Hubble's breakthrough didn't just prove the universe was expanding, it gave us a way to measure that expansion. By comparing redshift to distance calculated using pulsating stars called Cepheid variables, astronomers could determine the universe's expansion rate, now known as the Hubble constant. Yet this discovery raised even deeper questions. If galaxies are fleeing, does that mean everything was once crammed together? The answer, of course, pointed backward to the Big Bang, the moment when space, time, and all matter erupted from a single, unimaginable point. What's haunting is how much this revelation changed our place in the cosmos. We're not at the center of some static, eternal universe. We're adrift in an expanding sea, riding a wave of spacetime that's been stretching for 13.8 billion years. And every redshifted galaxy we observe is a backward glance in time, its light carrying whispers from an era when the universe was younger, hotter, and far more crowded. Hubble's discovery didn't just give us evidence of cosmic expansion, it handed us a time machine. Imagine holding a cup of coffee in your hands, feeling its warmth slowly fade as you sit there. That's the universe, but on a scale so vast it defies comprehension. From the unimaginable heat of the Big Bang to the icy void between galaxies today, the cosmos has been cooling for 13.8 billion years, and it's not done yet. Rewind to the universe's first moments, when temperatures soared to over 10 trillion degrees, so hot that matter couldn't even form. Protons and neutrons swam in a seething plasma of quarks and gluons, a primordial soup where particles collided with enough energy to recreate the conditions of a stellar core every fraction of a second. Then as space expanded, it stretched the energy thin, like spreading a campfire's warmth across an entire continent. Within minutes, temperatures dropped just enough for the first atomic nuclei to assemble, a process called Big Bang nucleosynthesis, the universe's first act of cosmic alchemy. Fast forward to 380,000 years later, and the temperature had plummeted to around 3,000 degrees, cool enough for electrons to finally latch onto those nuclei, forming the first atoms. This milestone, known as recombination, released the cosmic microwave background, the afterglow we now detect as a faint whisper of microwaves bathing the entire cosmos. That radiant heat, once blistering enough to vaporize planets, has since chilled to just 2.7 degrees above absolute zero, the coldest temperature possible. But here's the chilling truth: the universe isn't just cooling, it's accelerating toward a frigid fate. As dark energy pushes galaxies apart, the space between them grows, diluting the energy trapped within. Stars will eventually exhaust their fuel, black holes will evaporate over incomprehensible timescales, and the last remnants of heat will fade into darkness. Some theories predict a big freeze, where the cosmos reaches near uniform coldness, a state of maximum entropy where even time loses meaning. Yet this cooling isn't just a slow slide into oblivion, it's the reason we exist. Without that gradual loss of heat, matter would never have clumped into galaxies, stars, or planets. The universe's cooling curve is the silent architect of complexity, trading raw energy for the structures that make life possible. So the next time you feel a winter chill, remember, you're feeling a whisper of the cosmos' oldest story, the inevitable heat-death written into the fabric of reality itself. When we hear a Big Bang, most of us picture a cosmic bomb detonating in some dark void, a violent explosion hurling matter outward into empty space, but that mental image. It's fundamentally wrong. The Big Bang wasn't an explosion in space, it was the explosive birth of space itself, a moment when time, matter, and the very fabric of reality erupted into existence simultaneously. Here's the critical distinction. Explosions happen within a pre-existing environment, a firecracker bursts in air, a supernova tears through interstellar gas. But at the moment of the Big Bang, there was no outside, no empty stage for the universe to expand into. Space didn't spread into anything, it simply became, unfolding from an incomprehensibly hot, dense state into the vast cosmos we know today. Imagine blowing up a balloon covered in dots. As it inflates, the dots don't move across the surface, they're carried apart by the stretching rubber. That's closer to what the Big Bang really was, the balloon's material creating the surface as it expanded. This misunderstanding trips up even the most attentive minds because our instincts are rooted in everyday physics. We're used to objects moving through space, not space itself being the thing that's dynamic. But the evidence is etched across the sky. The cosmic microwave background, the afterglow of the Big Bang isn't radiating from one distant point, like the remnants of a blast. It's everywhere in all directions because the event didn't happen somewhere, it happened everywhere at once. Think of it like this: if you could rewind the universe, you wouldn't see galaxies racing back to a central point like shrapnel, returning to a grenade. Instead, you'd witness space itself shrinking, distances collapsing until all points in today's universe converge to a single, unfathomably hot speck. No edge, no center, just pure potential, a singularity where the rules of physics as we know them break down entirely. This realization reshapes how we understand cosmic history. The universe isn't expanding because it was launched by some primordial force, it's expanding because space itself is still stretching, carrying galaxies along like driftwood on a rising tide. And here's the kicker, that expansion doesn't need an outside to grow into. The math of general relativity allows space to curve back on itself, meaning the universe could be finite yet boundless, like the surface of a four-dimensional sphere. So next time someone mentions the Big Bang as a cosmic blast, remember, what we're really talking about is the moment space woke up, stretching itself into existence and setting the stage for every galaxy, star, and atom that would ever exist. The Big Bang didn't happen in space, it created space, and we're all still riding that initial wave of expansion today. Let's tackle one of the most dizzying ideas in cosmology, the possibility that the universe might be infinite. Not just big, not just vast, but truly without end, stretching forever in every direction. It's a concept that defies our everyday intuition, because everything in our experience has edges: books, buildings, even Earth itself. But the universe, it might play by entirely different rules. How could something be infinite? Start by picturing the observable universe, that 93 billion light-year bubble we can see. That's our cosmic horizon, the limit of what light has had time to reach us. But here's the catch, there's no reason to think that's all there is. In fact, multiple lines of evidence suggest the universe extends far beyond what we'll ever observe. Think of it like standing in the middle of an endless forest. Even if fog limits your view to just a few hundred feet in every direction, you know the trees keep going. The real question is whether that forest-hour universe eventually stops or rolls on without end. The strongest hint comes from geometry. As we've seen, measurements of the cosmic microwave background reveal a flat universe, where parallel lines never meet, and the angles of triangles add up to exactly 180 degrees. In an infinite universe, that flatness makes perfect sense. There's no curvature because there's no edge to bend around. It's like an infinite sheet of paper. No matter how far you go, the rules stay the same. But an infinite cosmos isn't just a mathematical quirk, it has mind-bending implications. For one, if space truly has no end, then somewhere out there, every possible configuration of matter must exist. That means there could be an infinite number of copies of you, reading an infinite number of variations of this script on infinite versions of Earth. It's a concept straight out of science fiction, yet it falls naturally out of the math. Even our most distant observable galaxies might just be the first few grains of sand on an endless beach. Here's where it gets even stranger. If the universe is infinite now, it was always infinite even at the Big Bang. That doesn't mean everything was infinitely large back then, though. Instead, imagine an infinite grid where every point was scrunched arbitrarily close together. The Big Bang wasn't an explosion from a single point, it was the simultaneous stretching of all points in that infinite grid. Space didn't expand into anything, it just got less dense everywhere at once. The catch we may never know for sure: an infinite universe looks identical to a finite but unimaginably vast one from our limited vantage point. Like ants trying to deduce the size of Earth by studying a picnic blanket, we're stuck drawing conclusions from a tiny slice of reality. But whether finite or infinite, one thing's certain: the true scale of existence humbles even the boldest imaginations. The universe doesn't owe us edges or endings, it might just go on forever, vast beyond comprehension, hiding its deepest nature in plain sight. The universe isn't just expanding, it's racing toward an inevitable end. But how exactly will it all conclude? Scientists have two leading theories, each more unsettling than the last. The first, known as heat death, paints a picture of slow, icy decay. Imagine a campfire reduced to embers, then ash, then nothing but cold, still air. Over trillions of years, stars will exhaust their fuel, galaxies will drift apart, and black holes will evaporate into faint whispers of radiation. Eventually, the cosmos will reach a state of maximum entropy, a lifeless equilibrium where no energy flows, no structures form, and time itself becomes meaningless. It's not a dramatic explosion or collapse, just an endless, silent twilight where even atoms might decay into their most basic particles. But there's another possibility, far more violent and abrupt: the Big Rip. If dark energy's repulsive force grows stronger over time, something current observations can't yet rule out, the universe's expansion could accelerate to unimaginable extremes. First, galaxies would be torn apart, their stars scattered into the void. Then solar systems would unravel, planets ripped from their orbits. In the final moments, even atoms would be shredded as the space between particles expands faster than the forces holding them together. The universe wouldn't just fade away, it would dissolve in a catastrophic instant, space-time itself torn asunder like tissue paper, stretched beyond its limits. What determines which fate awaits us? It hinges on dark energy's true nature. If its strength remains constant, heat death is the likely outcome, a slow, inevitable cooling. But if dark energy intensifies, the Big Rip becomes unavoidable. Right now, the data leans toward heat death, but the margin of error leaves room for doubt. It's like watching a train approach a fork in the tracks, unsure which path it will take until the last possible moment. Here's the chilling part: both scenarios erase any possibility of life's return. Heat death offers a frozen forever, while the Big Rip leaves no after at all. Yet there's an eerie beauty in these cosmic prophecies. They remind us that the universe, for all its grandeur, operates on borrowed time, a fleeting performance in an incomprehensibly vast theater. Whether it ends with a whimper or a scream, one thing's certain: the story of the cosmos has an expiration date, written in the invisible ink of dark energy's mysteries. Picture this: a faint glow fills every corner of the sky, invisible to your eyes but detectable with the right instruments. This isn't just any light, it's the cosmic microwave background, or CMB, the oldest photograph ever taken. Captured when the universe was a mere 380,000 years old, this afterglow is our most direct window into the fiery dawn of existence. Here's how it happened. In the universe's earliest moments, space was a seething plasma too hot for atoms to form, a thick soup of charged particles that scattered light like fog, obscuring a lighthouse. But as expansion cooled the cosmos, electrons finally latched onto protons, creating the first neutral hydrogen atoms. This event, called recombination, cleared the cosmic fog, allowing light to travel freely for the first time. That light, originally blazing at thousands of degrees, has been stretched by expanding space over billions of years, cooling to just 2.7 degrees above absolute zero. Today we detect it as microwave radiation, a whisper from the infant universe. Finding this relic wasn't easy. In 1965, radio astronomers Arno Penzias and Robert Wilson stumbled upon mysterious static interfering with their antenna at Bell Labs. After eliminating every possible source, even cleaning out pigeon nests, they realized the noise wasn't a flaw. It was the universe itself humming with remnants of its birth. Their accidental discovery earned them a Nobel Prize and transformed cosmology forever. Modern telescopes like the Planck satellite have mapped the CMB in breathtaking detail, revealing subtle temperature variations, hot and cold spots no larger than 1 part in 100,000. These tiny fluctuations are cosmic gold. They're the seeds of all structure in the universe, regions where matter was ever so slightly denser, destined to collapse under gravity and form galaxies. Without those imperfections, the cosmos would be a featureless void. What's astonishing is how ubiquitous this glow is. No matter where you point a radio telescope, the CMB is there, bathing Earth in microwaves from every direction. It's not coming from a place, it's coming from a time, a moment when the universe transitioned from opaque plasma to transparent space. The light hitting our detectors today has traveled for over 13 billion years, carrying fingerprints of the cosmos before stars or galaxies existed. Yet the CMB isn't just a relic, it's an active tool. By studying its polarization, scientists probe cosmic inflation's gravitational waves. Its temperature map tests theories of dark matter and energy. Even its slight redshift confirms universal expansion. This ancient light isn't frozen history, it's a dynamic record, still revealing secrets 13.8 billion years after its journey began. So the next time you hear static on an old TV, remember, about 1% of that snow is the birth cry of the universe, echoing across the eons. If you could shrink the entire observable universe down to the size of Earth, every galaxy we've ever detected would fit inside a single coffee cup. That's how staggeringly empty the cosmos truly is. Even in the densest galaxy clusters, where millions of stars huddle together, the average distance between them is so vast that colliding stars are nearly unheard of. Space is just too spacious. Take our own cosmic neighborhood. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. If the Sun were a grapefruit in New York City, Proxima would be another grapefruit near Los Angeles, with nothing but void in between. Scale that up to the Milky Way's 100,000 light-year diameter, and you're looking at a glittering disk where stars are like fireflies scattered across a continent, each unaware of the other's light. But galaxies themselves are just specks in the grand tapestry. The average distance between them is about 20 times their own size. Picture two marbles placed 3 feet apart. That's the scale of Andromeda and the Milky Way, separated by 2.5 million light-years of near-perfect emptiness. The Virgo supercluster, containing thousands of galaxies, is 99.9% void when you account for the mind-bending volumes between its threads. Why does this matter? Because this emptiness shapes everything. It's why the night sky is dark despite countless stars. Their light simply hasn't reached us yet across the gulf. It's why cosmic expansion can accelerate unchecked, with dark energy pushing against nothingness. Even atoms are mostly empty space. If a hydrogen atom were the size of a football stadium, its nucleus would be a pea on the 50-yard line. Emptiness isn't just around us, it's in us, the same void that fills the cosmos. Yet this vacuum is anything but simple. Quantum physics reveals that empty space seethes with virtual particles popping in and out of existence, a froth of energy that might hold the key to dark energy itself. So when we say the universe is mostly nothing, we're not talking about absence, we're talking about potential, the invisible stage where all of reality's dramas unfold. Time isn't just something that ticks forward in the universe, it's part of the universe's very fabric, woven into existence alongside space and matter during the Big Bang. This means asking what came before the Big Bang might be as meaningless as asking what's north of the North Pole. There was no before, because time itself hadn't begun yet. Think of it like this: imagine the universe as a novel. The Big Bang isn't just the first chapter, it's the moment the book itself was printed. Asking what happened before the Big Bang is like flipping back past the title page expecting more story, only to find blank paper. Time isn't an eternal stage where events unfold, it's more like the script itself, emerging from nothingness in that initial cosmic instant. Einstein's theory of general relativity gives us the mathematical backbone for this idea. Spacetime isn't static. It curves, stretches, and even warps around massive objects like stars and black holes. But if you rewind the tape far enough, you reach a point where spacetime becomes so compressed that the equations break down entirely. This singularity isn't just a tiny dot in space, it's the boundary where time itself ceases to function, where cause and effect lose all meaning. This doesn't stop physicists from speculating, of course. Some theories, like loop quantum gravity, suggest time might have rebounded from a previous universe's collapse, like a cosmic slingshot. Others propose that our universe is just one bubble in an endless multiverse foam, where time flows differently in each pocket. But here's the catch: without any observable evidence, no light, no particles, no gravitational waves that could have crossed over from a pre-Big Bang era, these ideas remain untestable poetry. The implications ripple through everything we know. If time had a beginning, it might also have an end, not just in the heat death of the universe, but as a fundamental property that could one day dissolve. It reshapes how we think about eternity, creation, and even the nature of existence. We're not just living in time, we're living because of it, riding a wave that started 13.8 billion years ago when the cosmic clock first started ticking. What if our universe isn't alone, not just in the sense of distant galaxies, but as one bubble in an endless cosmic froth, a single reality among countless others, each with its own rules, its own physics, even its own version of time? This is the multiverse theory, one of the most provocative ideas in modern cosmology, and it's not just science fiction. Some of the world's leading physicists argue that our universe might be one page in an infinite cosmic library, where every possible variation of physical laws exists somewhere in the greater whole. The idea springs from multiple branches of physics. Inflation theory, for instance, suggests that the rapid expansion of the early universe didn't just happen once, it could be ongoing in other regions of space, spawning new universes like bubbles in a boiling pot. Each of these bubble universes might cool differently, crystallizing their own unique laws of physics. In one, gravity could be 10 times stronger. In another, electromagnetism might not exist at all. Some could be barren, devoid of the delicate balances that allow atoms or stars to form, while others might harbor life in forms we can't even imagine. Then there's string theory, which proposes that the fundamental particles we know are actually tiny, vibrating strings. To make the math work, string theory requires at least 10 dimensions, far more than the 4 we experience. But where are these extra dimensions? One possibility is they're curled up too small for us to detect, like the grooves on a vinyl record too fine for a needle to feel. In this framework, different configurations of those hidden dimensions could correspond to different universes, each with its own physics encoded in the geometry of unseen space. Even quantum mechanics hints at parallel realities. The many worlds interpretation suggests that every time a quantum particle makes a random choice, like whether to spin left or right, the universe splits, creating alternate timelines where each possibility plays out. In one branch you might be reading this script, in another you never clicked on this video at all. While this version of the multiverse deals with branching timelines rather than separate physical universes, it paints a similarly dizzying picture, a fractal tree of realities where every conceivable outcome exists somewhere. But how could we ever prove something so extravagant? Some scientists look for bruises in the cosmic microwave background, anomalies where our universe might have collided with another bubble long ago. Others search for subtle gravitational echoes or unexpected particle behavior that could betray the presence of hidden dimensions. So far, no smoking gun has been found, and critics argue that the multiverse theory strays dangerously close to untestable speculation. After all, if other universes are forever beyond our reach, does the idea hold any scientific weight? Yet the multiverse isn't just a wild guess, it's a natural extension of our best theories about how reality works. It solves puzzles like why our universe's constants seem fine-tuned for life. If infinite universes exist, then of course we'd find ourselves in one where conditions allow our existence. It's the cosmic equivalent of a lottery. With enough tickets, even the most unlikely outcome becomes inevitable somewhere. Whether the multiverse is real or not, the idea stretches our imagination to its limits. It forces us to confront the possibility that everything we know, every galaxy, every law of physics, even the concept of everything itself, might just be a tiny corner of a reality too vast for comprehension. And that's the most humbling thought of all. Our universe, for all its grandeur, could be just one note in an infinite symphony. Back in 1998, two teams of astronomers made a discovery so shocking it upended decades of cosmic predictions, one that would later earn them the Nobel Prize. They weren't hunting for revolutionary truths, they were simply measuring distant supernovae, the explosive deaths of massive stars, to pin down how fast the universe was expanding. Conventional wisdom said gravity, the great cosmic glue, should have been slowing everything down, pulling galaxies back like a stretched rubber band resisting tension. But the data told a different story. Instead of slowing, the universe's expansion was speeding up, as if some invisible force had flipped gravity's script and turned it into a repulsive push. The key to this revelation lay in a particular type of supernova-type Ia known as cosmic, standard candles. These explosions shine with such predictable brightness that astronomers can calculate their distance just by measuring how dim they appear from Earth. By comparing these distances to the supernova's redshifts, how much their light stretched as space expanded, the teams expected to see the universe's expansion rate dropping over time. Instead, they found the most distant supernovae were dimmer than expected, meaning they'd been carried farther away by an expansion that wasn't just continuing, it was accelerating. It was like tossing a ball into the air and watching it shoot faster into the sky instead of falling back down. The implications were staggering. Not only was the universe not slowing down, but some mysterious energy dubbed dark energy was overpowering gravity's pull, stretching spacetime itself faster and faster. This wasn't just a tweak to existing models, it was a fundamental rewrite of cosmic destiny. For decades, scientists had debated whether the universe would eventually collapse in a big crunch or expand forever into cold darkness. Now a third option emerged, one where expansion accelerates so relentlessly that distant galaxies vanish over the horizon, leaving future astronomers with a sky bereft of anything beyond our local cluster. What makes this acceleration even stranger is its timing. For the first 9 billion years, gravity dominated, and expansion did slow down, just as expected. But around 5 billion years ago, as galaxies grew farther apart and matter's grip weakened, dark energy took the wheel. Now it's calling the shots, pushing galaxies apart at speeds that will one day rip them from our view entirely. The universe, it seems, has a foot on the gas pedal with no intention of lifting it. This discovery didn't just earn a Nobel Prize, it exposed how little we understand about the cosmos. Dark energy remains physics' most embarrassing open secret, a force making up 68% of the universe's energy budget, yet completely invisible to our detectors. Is it the energy of empty space itself, as Einstein once suggested with his cosmological constant, or something far more exotic, like a fluctuating quantum field? Whatever it is, one thing's clear: the universe isn't just expanding, it's running away from us, and we're only beginning to understand why. Imagine measuring the speed of a car with two different radar guns, only to get conflicting results by just a few miles per hour. That's essentially the headache astronomers face with the Hubble constant, the number that tells us how fast the universe is expanding. The weird part: this isn't some tiny discrepancy lost in decimal places. Depending on how you measure it, the universe's expansion rate varies by enough to keep cosmologists awake at night, scratching their heads over what they might have missed. The tension starts with two primary ways to pin down this number. The first method relies on the cosmic microwave background, the afterglow of the Big Bang. By studying its subtle wrinkles with spacecraft like Planck, scientists can extrapolate how fast space should be stretching today. Their answer: roughly 67 kilometers per second per megaparsec, meaning for every 3.3 million light years you look out into space, galaxies appear to recede 67 kilometers per second faster. But here's where things get spicy. The second method skips ancient light entirely and focuses on nearby stars and supernova. By tracking the pulsations of Cepheid variable stars, nature's cosmic yardsticks, and pairing them with Type Ia supernova, teams like the one using the Hubble Space Telescope land on a different number, 73 kilometers per second per megaparsec. That 7% gap might seem small, but in a field where precision is everything, it's like realizing two blueprints for the same bridge disagree on whether it'll reach the other side. So who's right? The answer could rewrite our understanding of physics. Maybe dark energy isn't constant but evolves over time, throwing off our measurements. Or perhaps undiscovered particles are tweaking the early universe's behavior. Some theorists even flirt with the idea that we're seeing cracks in Einstein's gravity itself, hints that relativity needs an update when applied to the cosmos at large. The stakes are cosmic. If the CMB measurements hold, our models of the universe's infancy might be flawless, but if local observations win, we're staring at a puzzle with missing pieces, a tantalizing clue that there's still something fundamental we don't grasp about how space stretches. Until someone reconciles these numbers, the Hubble constant remains less a fixed rule and more a question written across the sky, challenging us to look deeper. Deep within the fiery chaos of the early universe, hidden beneath the unimaginable heat and density of the Big Bang, tiny quantum fluctuations flickered into existence, random ripples in the fabric of reality, so small they'd make an atom look like a galaxy. Yet these infinitesimal blips held the blueprint for everything we see today: the sprawling cosmic web of galaxies, the vast voids between them, even the stars lighting up the night sky. All of it traces back to those fleeting quantum tremors, stretched to cosmic proportions by the universe's explosive growth. Picture the infant universe as a pot of boiling water, its surface constantly churning with bubbles forming and popping at random. On the quantum scale, pairs of particles and antiparticles blinked in and out of existence, borrowing energy from the vacuum before vanishing again. Normally, these fluctuations cancel each other out almost instantly, but in the universe's first fraction of a second, something extraordinary happened: cosmic inflation, that hyper-fast expansion, seized these tiny irregularities and stretched them across light years, freezing them into the very structure of space itself. What began as subatomic quantum noise became the seeds for matter's uneven distribution, like microscopic bumps on a balloon magnified as it inflates to the size of a city. Fast forward a few 100,000 years, and these once tiny ripples began pulling matter together, slightly denser regions, where those primordial fluctuations had piled up an extra handful of particles, exerted a stronger gravitational tug, drawing in gas and dark matter like cosmic whirlpools. Over billions of years, these knots grew into the first stars, then galaxies, then galaxy clusters, while the emptier regions expanded into the vast voids we see today. The proof it's written in the cosmic microwave background, where temperature variations as small as 1 part in 100,000 reveal the exact pattern of those quantum seeds, imprinted like fossils in the afterglow of creation. Here's the wildest part: without these quantum fluctuations, the universe would be a featureless wasteland. No galaxies, no stars, no planets, just a perfectly smooth, utterly boring soup of particles. The very existence of structure depends on those random flickers, amplified by inflation into the scaffolding of reality. It's as if the universe rolled a quantum dice at its birth, and the outcome determined where every galaxy would form billions of years later. Yet this raises a profound question: if those fluctuations were truly random, why do they follow such a predictable statistical pattern? Scientists call this the primordial power spectrum, a fingerprint showing that quantum noise scales in a specific way across different sizes, like finding ocean waves of all heights still obeying a hidden mathematical rule. Some theories suggest this pattern hints at deeper physics, perhaps even echoes of quantum gravity or hidden dimensions tweaking the early universe's behavior. What's certain is this: the quantum ripples that birth the cosmos remind us how deeply interconnected reality is. The same physics governing particles in a lab today once shaped the universe on the grandest scales, linking the microscopic to the cosmic in a chain of cause and effect spanning billions of years. Every galaxy, every star, every planet including ours is the end result of quantum dice rolled in the first moments of time, a cosmic lottery where randomness somehow wrote the recipe for everything. 13.8 billion years, that's the universe's current best documented birthday, a number etched into textbooks and telescopes alike. But pinning down the age of something as vast as the cosmos isn't as simple as counting tree rings or radioactive decay. Instead, scientists had to become cosmic detectives, piecing together clues from the universe's own expansion and the faint echoes of its fiery infancy. The first critical clue came from Edwin Hubble himself. By measuring how fast galaxies are receding from us, their redshifts, he revealed the universe was expanding. But to turn that expansion rate into an age estimate, cosmologists needed to rewind the tape, imagining all galaxies hurtling backward until they'd converge at a single point. Think of it like hitting rewind on a fireworks display, watching every spark shrink back to the moment of ignition. The faster the expansion, the less time it would have taken to reach today's sprawl, making the universe younger. Early calculations using Hubble's initial data suggested a mere 2 billion years, a figure so awkwardly short it was younger than some geologic rocks on Earth. Clearly, something was missing. Enter the cosmic microwave background, the universe's baby picture. When the Planck satellite mapped the CMB's subtle temperature variations with unprecedented precision, it gave scientists a Rosetta Stone for decoding cosmic history. Those tiny hot and cold spots encode the universe's density, composition, and expansion rate at just 380,000 years old. By plugging these measurements into Einstein's equations of general relativity, researchers could simulate how the universe evolved from a seething plasma to today's galactic tapestry. The result, a staggeringly consistent age estimate, 13.8 billion years, give or take a mere 40 million. That's like determining the age of a century-old person with an accuracy of 3 months. But here's where it gets elegant. The CMB and Hubble constant methods aren't independent. They are two sides of the same cosmic coin. The Hubble constant tells us how fast space is stretching now, while the CMB reveals how that stretch rate has changed over time, slowed by gravity, and later accelerated by dark energy. It's like calculating how long a car trip took by knowing both the current speed and how often the driver hit the brakes or gas. When both methods agree within error margins, it's a triumph of cross-verified science. Yet this age isn't just a number, it's a yardstick for everything else. It tells us when the first stars flickered on around 200 million years after the Big Bang, when galaxies began clustering a few billion years later, and even how old the oldest known star, Methuselah, can possibly be no older than the universe itself, despite early estimates that hilariously suggested otherwise. 13.8 billion years is more than a statistic. It's the ultimate timeline, the backbone of cosmic history, and a humbling reminder that everything we see is just the latest frame in an epic still unfolding. Somewhere in the depths of space, hidden behind the thick veil of stars and dust near the Milky Way's core, an invisible force is pulling thousands of galaxies, including our own, toward it at breakneck speeds. Astronomers call it the Great Attractor, and it's one of cosmology's most perplexing puzzles. Imagine floating in a river where all the currents mysteriously converge toward a single point, dragging everything along with them, yet you can't see what's causing the pull. That's precisely the situation we're in with this gravitational enigma. The story begins in the 1970s, when astronomers mapping galaxy motions noticed something bizarre. The Milky Way, along with our entire local group of galaxies, isn't just drifting aimlessly through space, it's racing toward a specific patch of sky in the constellation Centaurus at over 600 kilometers per second. At first, scientists assumed this motion was just part of the universe's overall expansion, but detailed calculations revealed an extra tug, a gravitational override steering galaxies off their expected paths. Something massive, unseen, uncharted, was warping the flow of cosmic traffic on a scale of hundreds of millions of light years. Here's where it gets even stranger. The Great Attractor lies in what astronomers call the zone of avoidance, a region obscured by the dense stars, gas, and dust of the Milky Way's galactic plane. It's like trying to spot a lighthouse through a blizzard. Our own galaxy's bulk blocks the view. Early X-ray and infrared telescopes could barely penetrate this cosmic blind spot, leaving the attractor's true nature shrouded in speculation. Was it a supercluster of galaxies, a concentration of dark matter so dense it defied imagination, or something even more exotic? Breakthroughs came when astronomers looked beyond the Great Attractor itself. By studying the trajectories of galaxies behind it, they discovered an even larger structure, the Laniakea supercluster, a web of galaxies spanning 500 million light-years, with the attractor acting as its gravitational anchor. Think of it as a mountain in a vast landscape, drawing rivers of galaxies toward its slopes. Yet even Laniakea's colossal mass couldn't fully explain the observed pull, hinting that something even grander might lurk in the shadows, a cosmic puppeteer we've yet to identify. The mystery deepens when you consider dark energy's role. In a universe where space itself is stretching apart, how did such a concentrated gravitational anomaly form? Some theories suggest the Great Attractor could be a remnant of the early universe's density fluctuations, a knot in spacetime that survived inflation. Others propose it's a dark flow, a ripple from a collision with another universe in the multiverse, though that remains speculative. What's certain is this: the Great Attractor forces us to confront how little we know about the large-scale structure of the cosmos. It's a reminder that even as we peer billions of light-years into space, some of the universe's biggest secrets might be hiding in plain sight, masked by the glow of our own galactic backyard. And until we develop tools to see through the zone of avoidance, This gravitational siren will keep pulling us toward answers just out of reach. Long before galaxies and stars filled the cosmos, the universe was a roiling sea of plasma so dense that light couldn't travel more than a fraction of an inch before scattering. White-hot fog where sound waves, not light, carried information. These primordial sound waves, known as baryon acoustic oscillations, left permanent scars on the structure of the universe, fingerprints we can still detect today in the precise spacing between galaxies billions of years later. Here's how it worked. In the first few 100,000 years after the Big Bang, the universe was a tightly coupled soup of protons, electrons, and photons, constantly colliding. Gravity tried to pull matter together into clumps, while the intense radiation pressure of light pushed back, creating a tug-of-war that generated rhythmic compression waves, cosmic echoes rippling through the plasma like sound waves through air. These pressure waves traveled outward at nearly half the speed of light, creating spherical shells of densely packed matter. Then when the universe cooled enough for atoms to form and light broke free, what we see today as the cosmic microwave background, those waves froze in place, leaving behind a distinctive pattern, clusters of matter separated by a characteristic distance, like rings on a pond after a stone drops in. That distance, about 500 million light-years, became a cosmic ruler etched into the fabric of space. As the universe expanded, galaxies formed preferentially along those ancient ripple crests, meaning today's large-scale structure still bears that imprint. When astronomers map millions of galaxies, they don't see random scatter. They find a subtle excess of pairs separated by that same 500 million light-year scale, a ghostly echo of sound waves from the universe's infancy. This phenomenon isn't just a fossil, it's one of our most powerful tools for measuring cosmic expansion. Unlike supernova or Cepheid stars, baryon acoustic oscillations don't rely on understanding a celestial object's brightness. Instead, they act as a standardized ruler. By measuring how much that 500 million light yardstick appears stretched or compressed at different cosmic eras, scientists can calculate how much space has expanded over billions of years. It's like finding a series of identical footprints in wet concrete, some close together, others farther apart, and deducing how much the concrete stretched as it dried. What makes this technique so revolutionary is its precision. While dark energy's discovery relied on a few hundred supernova, projects like the Sloan Digital Sky Survey have mapped over 1 million galaxies, using baryon acoustic oscillations to pin down expansion rates with unprecedented accuracy. They've confirmed dark energy's dominance and even shed light on the Hubble tension, that nagging discrepancy between early and late universe expansion measurements. But perhaps the most astonishing thing about these cosmic sound waves is how enduring they are. For 13.8 billion years, through the birth of stars, the death of galaxies, and the relentless stretching of space, that primordial rhythm has persisted, a beat first struck when the universe was a seething plasma, now guiding our understanding of its ultimate fate. We've mapped dark matter, charted dark energy, but here's a cosmic detective story that rarely makes headlines. Half the universe's ordinary matter is missing. Not exotic particles, not invisible forces, but the same protons and neutrons that make up stars, planets, and even you. Based on meticulous calculations of the early universe's composition, scientists know exactly how much of this baryonic matter should exist today. Yet when they tally up all the visible galaxies, gas clouds, and cosmic dust, nearly half of it has vanished without a trace. The mystery begins with the cosmic microwave background. Those ancient temperature fluctuations don't just reveal the universe's age, they are also a precise ledger of its original matter content. By measuring how sound waves propagated through the early plasma, physicists determined baryons should account for about 5% of the universe's total energy budget. Fast forward 13 billion years, and all the stars, galaxies, and interstellar gas we can detect only add up to roughly half that amount. It's as if someone took every other atom in the cosmos and erased it from existence. Where could it all be hiding? One leading theory points to the vast webs of warm hot intergalactic medium, or WIM filaments of ionized gas threading between galaxies, so diffuse they're nearly invisible. Picture trying to spot a single strand of spider silk stretched across a football field. That's the challenge astronomers face. Yet recent X-ray telescopes like Isaac Newton have begun detecting faint glows from oxygen atoms in these tendrils, heated to millions of degrees and stretching millions of light years. Some estimates suggest this cosmic cobweb might hold 30 to 40% of the missing matter, woven into the voids we once thought were empty, but the plot thickens. Even accounting for WIM, there's still a gap. Enter another suspect, fast radio bursts. These millisecond-long cosmic flashes, likely emanating from distant neutron stars, disperse slightly as they traverse intergalactic space. By measuring this dispersion, astronomers can estimate the electrons they've encountered along the way, and thus the density of invisible matter in their path. In 2020, one such burst revealed a startling surplus of baryons in the space between galaxies, potentially closing part of the deficit. The final piece might lurk in our own cosmic backyard. Supercomputer simulations suggest some missing matter could be hiding in our galaxy's halo as ultra-diffuse gas clouds, too cold to emit detectable radiation. Others propose it's been blasted out of galaxies by supernova, forming a mist of high-energy particles too faint for current instruments. Whatever the answer, this isn't just bookkeeping, it's a fundamental test of whether we understand how matter assembles across cosmic time. What's breathtaking is how close we are to solving this. Upcoming observatories like the James Webb Space Telescope and the Square Kilometre Array will probe these dark reservoirs with unprecedented sensitivity. Every atom they find brings us nearer to balancing the universe's ledgers, and perhaps uncovering new physics along the way. After all, if half the ordinary stuff in creation can vanish without explanation, what other surprises might be hiding in plain sight? Right now, the universe is a dazzling tapestry of light, with stars igniting across galaxies in a cosmic fireworks show that's lasted billions of years. But this golden age of star formation won't last forever. In fact, the universe is on a slow, inevitable march toward darkness, a future so distant it defies imagination, where the last star will flicker out, leaving galaxies as graveyards of cold, dead suns. The culprit, cosmic expansion, fueled by dark energy's relentless push. As galaxies drift farther apart, the raw material for new stars' clouds of hydrogen gas becomes increasingly scattered. Imagine trying to light a campfire in a windstorm, with gusts blowing your kindling away faster than you can gather it. That's the fate awaiting future galaxies. Already, the rate of star birth has dropped dramatically since the universe's early heyday, when galaxies churned out stars 20 times faster than they do today. But in trillions of years, even the most gas-rich galaxies will exhaust their reserves, their stellar assembly lines grinding to a halt. The last stars to form will be small, dim red dwarfs, the universe's thrifty candle savers. Unlike our sun, which will burn out in a mere 10 billion years, these frugal stars sip their hydrogen fuel so slowly they could shine for trillions of years. But even they aren't eternal. As the universe expands, pulling galaxies beyond each other's gravitational reach, the intergalactic gas needed to birth new stars will be stretched too thin to clump together. No collapses, no protostars, no nuclear ignition, just an ever-cooling void where the recipe for star formation has been lost. What's left will be a haunting tableau. Galaxies once vibrant with starlight will darken as their remaining stars die. White dwarfs will cool into black dwarfs, neutron stars will fade, and black holes will loom like silent sentinels in the abyss. The cosmos will enter the degenerate era, where the only energy comes from the rare collision of failed stars or the ghostly glow of particle decay. Even the Milky Way, our own galactic home, will be unrecognizable, its spiral arms dissolved, its stars scattered, its light extinguished. Yet this isn't the universe's final chapter. Black holes will dominate for epochs beyond counting, slowly evaporating via Hawking radiation until they too dissolve into nothingness. The last visible structures will vanish, and space will settle into a state of maximum entropy, a featureless sea of particles so far apart they might as well be alone. The era of stars, those brilliant beacons that made life possible, will be just a fleeting spark in the cosmic night. But here's the strange comfort in this cosmic twilight. Even as the universe grows cold and dark, the atoms forged in stars, the carbon in our cells, the oxygen we breathe will still drift through space, remnants of a time when the cosmos blazed with light. In a way, we're made of stardust from a universe that once knew how to shine. What if everything you see, the stars, the planets, even your own hands, is nothing more than an illusion, a cosmic mirage projected from some hidden, lower-dimensional reality? This isn't science fiction, it's the holographic principle, one of the most mind-bending ideas in modern physics. The theory suggests our three-dimensional universe, with all its depth and solidity, might actually be encoded on a distant, two-dimensional surface, like a movie playing on an immeasurably vast celestial screen. The concept emerged from an unexpected place, black hole physics. In the 1970s, physicist Jacob Bekenstein discovered that black holes possess entropy, a measure of disorder, and that this entropy isn't determined by their volume, as you'd expect, but by their surface area. Later, Stephen Hawking confirmed that black holes emit radiation, meaning they can lose mass and eventually evaporate. But here's the puzzle: if a black hole disappears, what happens to all the information it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity suggests it vanishes forever. The holographic principle offered a way out. What if the information isn't lost because it was never truly inside the black hole to begin with? Instead, it's painted on the event horizon, the black hole's two-dimensional boundary, like a cosmic fresco preserving every detail of what fell in. This revelation sparked a radical shift in how we think about reality. If a black hole's entire contents can be encoded on its surface, could the same be true for the universe? Imagine the cosmos as a giant bubble. The holographic principle proposes that all the information describing every particle, every force, every event within that bubble is somehow stored on its outer shell. We're not just in the universe, we might be the universe's own projection, a 3D rendering of data written on a 2D surface at the edge of everything. But how could this possibly work? Think of a credit card hologram, a flat sticker that creates a 3D image when tilted. In a similar way, the universe might tilt the information encoded on its boundary into the full richness of our experience. String theory and quantum gravity models suggest that the fabric of spacetime could emerge from tiny, interconnected bits of information, much like pixels on a screen. The key difference: these pixels would be unimaginably small, around a Planck length in size, or 10 to the power of -35 meters. At this scale, the distinction between inside and outside blurs, and dimensionality itself becomes fluid. What's astonishing is that this idea isn't untestable. Physicists have already found hints of holography in the way quantum fields behave near black holes. Experiments using gravitational wave detectors and particle accelerators might one day uncover subtle anomalies, tiny deviations from classical physics that could reveal the universe's pixelated, holographic nature. Even the cosmic microwave background could hide patterns pointing to a deeper, two-dimensional code underlying reality. The implications are staggering. If the holographic principle is true, it means our perception of depth, distance, and solidity is a grand illusion, a trick of the cosmic light. It would rewrite our understanding of everything from the birth of the universe to the nature of consciousness itself. After all, if the brain is just part of the projection, where does that leave the mind? The holographic principle doesn't just challenge our place in the cosmos, it redefines what the cosmos even is. One thing's certain: if reality is a hologram, We're all part of the most spectacular show in existence, an epic written in 2 dimensions, performed in 3, and waiting for us to decode its script. Of all the mysteries in the cosmos, this one hits closest to home. Why does the universe seem tailor-made for our existence? Tweak the strength of gravity by just 1%, and stars would never ignite. Adjust the cosmic expansion rate slightly, and matter would either fly apart or collapse before life could arise. Even the nuclear forces binding atoms follow such exacting rules that altering them would render chemistry, and therefore biology, impossible. This eerie precision is called the anthropic principle, the idea that the universe's fundamental constants appear fine-tuned because, well, we're here to notice them. Think of it like a cosmic lottery with impossibly long odds. The gravitational constant, the speed of light, the mass of an electron, each of these values could theoretically vary across infinite possibilities. Yet somehow we find ourselves in the one version where every dial is set just right for atoms, planets, and conscious life. It's as if the universe's instruction manual had a single, perfect set of parameters for building creatures who could read it. This revelation forces us to confront profound questions. Does this apparent fine-tuning imply a designer? Not necessarily. One explanation is the multiverse. If infinite universes exist with random physical laws, statistically, some must hit the jackpot for life. We're simply in the one that did. Others suggest deeper laws might someday reveal why these constants couldn't have been different, making fine-tuning inevitable. Then there's the radical possibility that consciousness itself plays a role in shaping reality, that the universe requires observers to give it meaning. Yet beyond philosophy, the anthropic principle reshapes how we search for life. It suggests that even in a vast, indifferent cosmos, the very laws permitting our existence might make us less alone than we think. If the universe is this hospitable here, why not elsewhere? But it also carries a humbling truth: we're not the center of creation, just beneficiaries of its precise balance. The stars don't shine for us, but without their exact nuclear furnaces, we wouldn't be here to see them at all. In the end, the anthropic principle isn't just about physics, it's a mirror. Staring into it, we see reflected back the staggering unlikeliness of our moment in the cosmos, balance between chaos and order, between chance and necessity. Whether by accident, design, or some deeper logic we've yet to uncover, the universe whispers a single haunting question: if the constants were any different, who or what would be here to wonder about them? From the universe's breakneck expansion, outrunning the speed of light, to the chilling reality of dark energy's accelerating push, we've journeyed through 25 cosmic revelations that stretch the limits of imagination. We've explored how quantum ripples birthed galaxies, how a 2-dimensional boundary might encode our 3D reality, and how the very laws of physics seem fine-tuned for life, yet half the universe's ordinary matter remains missing in action. These aren't just abstract curiosities, they're pieces of a puzzle that redefine our place in the cosmos, showing us a reality far stranger and more wondrous than we ever anticipated. But here's the humbling truth: for every mystery we've unraveled, a dozen more lurk in the shadows. We still don't know what dark matter truly is, why dark energy dominates the cosmos, or whether we're alone in a multiverse teeming with alternate realities. The great attractor's gravitational pull remains unexplained, the Hubble tension defies reconciliation, and the holographic principle challenges our most basic perceptions of existence. The universe, it seems, is a master of illusion, revealing just enough to keep us chasing the next revelation. So what's next? That's where you come in. The most thrilling chapters of this story haven't been written yet. They're waiting for the next generation of telescopes, experiments, and perhaps your curiosity to crack them open. Maybe you'll be the one to spot the first glimmer of a parallel universe, or decode the whispers of those primordial quantum fluctuations. Until then, keep looking up, questioning, and marveling at the fact that we're here at all. conscious and curious in a cosmos that's still learning to introduce itself. If these mysteries left you as awestruck as they left us, hit that subscribe button. We're just getting started. The universe has endless secrets to share, and we'll be here to unpack them, one mind-blowing discovery at a time. Until then, remember, every time you gaze at the night sky, you're not just seeing stars, you're staring into the greatest unsolved story of all, written in the language of dark matter, starlight, and the relentless expansion of space itself. And that's a story worth following to the very end.